The National Electrical Code, or NEC, does not explicitly prohibit the use of a transformer with a secondary voltage of 115 volts three-phase without a neutral, often referred to as a delta connection. However, several safety concerns must be considered. Firstly, unintentional neutral connection is a significant hazard. Because there is no neutral wire, if an outlet or device is improperly wired, a phase wire could be mistakenly connected as a neutral, creating a dangerous condition. Secondly, an unbalanced load is also a concern. A three-phase delta system inherently has no neutral wire to balance the load, which can result in unbalanced currents and potential overloads on one or more phases. Thirdly, equipment damage is possible. Connecting single-phase loads, such as 115-volt outlets, to a three-phase delta system can damage the equipment or cause malfunctions. While the NEC does not specifically prohibit this configuration, it does require that electrical installations be safe and comply with general wiring methods and standards. Several code sections may be applicable. NEC Section 404.1 requires balanced loads on three-phase systems. NEC Section 408.3 requires proper grounding and neutral connections. NEC Section 210.4 requires outlets to be properly wired with a grounded neutral conductor. Based on these safety concerns, it is generally not recommended to use a transformer with a secondary voltage of 115 volts three-phase without a neutral connection. If a three-phase delta system is required, it should include a neutral wire to ensure proper load balancing, grounding, and safety. The absence of a neutral in a three-phase delta system presents several challenges when attempting to power single-phase loads like standard 115 volts outlets. The core issue stems from the inherent imbalance that single-phase loads introduce to a three-phase system designed to operate with balanced loads. In a balanced three-phase system, the current in each phase is equal in magnitude and 120 degrees apart in phase angle. This balance ensures that the vector sum of the currents at any given time is zero, minimizing neutral current and optimizing system performance. However, when single-phase loads are connected to a delta system, they draw current from only two of the three phases at any given time. This creates an imbalance, as one phase may be heavily loaded while the other two are lightly loaded or unloaded. This imbalance can lead to several problems, including voltage imbalances, increased line losses, and potential overheating of transformers and conductors. Voltage imbalances occur when the voltage levels across the three phases are no longer equal. This can cause erratic operation of sensitive electronic equipment and reduce the efficiency of motors and other inductive loads. Increased line losses result from the higher currents flowing in the more heavily loaded phases. These higher currents cause increased resistive losses in the conductors, wasting energy and generating heat. Overheating of transformers and conductors can occur if the imbalance is severe enough. Transformers are designed to operate with balanced loads, and significant imbalances can cause excessive currents in certain windings, leading to overheating and potential failure. Similarly, conductors can overheat if they are carrying currents beyond their rated capacity. The NEC addresses these concerns through various provisions aimed at ensuring balanced loading and proper grounding. Section 404.1, as mentioned, emphasizes the importance of balanced loads on three-phase systems. While it may not explicitly prohibit single-phase loads on a delta system, it implies that steps must be taken to mitigate the resulting imbalance. This can be achieved through careful load planning, distribution of single-phase loads across all three phases, and the use of balancing transformers or other corrective measures. Section 408.3 requires proper grounding and neutral connections. In a delta system, grounding is typically achieved through a corner grounded delta configuration or a high resistance grounded delta configuration. However, neither of these configurations provides a neutral conductor for single-phase loads. Attempting to derive a neutral from one of the phase conductors can create a dangerous situation, as it effectively turns that phase conductor into neutral, potentially exposing personnel to low voltage. Section 210.4 requires outlets to be properly wired with a grounded neutral conductor. This requirement is difficult to meet in a delta system without a neutral. While it may be possible to use a separately derived system, such as a zigzag transformer, to create a neutral, this adds complexity and cost to the installation. Given these challenges, it is generally not recommended to use a delta system to power single-phase loads like standard 115 volts outlets. A more suitable approach is to use a Y-connected transformer, which provides a neutral conductor that can be used to supply single-phase loads. A Y-connected system allows for balanced loading, proper grounding, and compliance with NEC requirements for grounded neutral conductors at outlets. If a delta system is unavoidable, careful consideration must be given to load balancing, grounding, and the potential hazards associated with single-phase loads. It may be necessary to consult with a qualified electrical engineer to develop a safe and code-compliant solution. In addition to the specific NEC sections mentioned, other relevant codes and standards may apply depending on the specific application and location. These may include local building codes, industry standards, and equipment manufacturers' recommendations. It is important to consult all applicable codes and standards to ensure safe and compliant installation. Furthermore, it is crucial to use properly rated and listed equipment. Transformers, conductors, and other electrical components must be rated for the voltage, current, and environmental conditions in which they will be used. Using substandard or improperly rated equipment can increase the risk of failure, fire, and electrical shock. Regular inspection and maintenance are also essential for ensuring the continued safe operation of a three-phase electrical system. Electrical systems should be inspected periodically by qualified personnel to identify any potential problems, such as loose connections, damaged insulation, or overloaded circuits. Maintenance should be performed as needed to correct any deficiencies and prevent future problems. The implications of using a 115 volts three-phase delta system without a neutral are significant, primarily revolving around safety, code compliance, and equipment performance. Let's delve deeper into each of these areas. From a safety perspective, the absence of a neutral in such a system creates several potential hazards. One major concern is the risk of unintentional neutral connections. In the typical 115 volt single-phase system, the neutral wire provides a safe return path for current, and it is typically grounded to provide a low impedance path for fault currents. However, in a delta system without a neutral, there is no dedicated return path. If an outlet or device is improperly wired, a phase wire could be mistakenly connected as a neutral. This could energize the equipment chassis or enclosure, creating a shock hazard for anyone who comes into contact with it. Furthermore, the lack of a neutral can make it difficult to detect ground faults. In a grounded system, a ground fault will typically cause a large current to flow, tripping a circuit breaker or ground fault circuit interrupter, or GFCI, and interrupting the power supply. However, in a delta system without a neutral, a ground fault may not be readily detectable, as the fault current may be limited by the system impedance. This could allow the fault to persist undetected, potentially leading to equipment damage or even a fire. Another safety concern is the potential for voltage imbalances. As mentioned earlier, single-phase loads on a delta system can create voltage imbalances, which can cause erratic operation of sensitive electronic equipment and reduce the efficiency of motors and other inductive loads. In extreme cases, voltage imbalances can even damage equipment. From a code compliance standpoint, using a 115 volts three-phase delta system without a neutral can be problematic. While the NEC does not explicitly prohibit such a system, it does contain numerous requirements for grounding, neutral connections, and balance loading. Meeting these requirements can be challenging in a delta system without a neutral. For example, NEC section 250.20 generally requires that electrical systems be grounded. However, grounding a delta system without a neutral can be difficult, as there is no obvious point to connect to ground. While corner grounded delta and high resistance grounded delta configurations are possible, they may not be suitable for all applications. NEC section 210.4 requires that outlets be properly wired with a grounded neutral conductor. This requirement is difficult to meet in a delta system without a neutral, as there is no neutral conductor to connect to the outlet. While it may be possible to use a separately derived system, such as a zigzag transformer, To create a neutral, this adds complexity and cost to the installation. From an equipment performance perspective, using a 115 volts three-phase delta system without a neutral can also have negative consequences. As mentioned earlier, single-phase loads on a delta system can create voltage imbalances, which can reduce the efficiency of motors and other inductive loads. Voltage imbalances can also cause increased heating in transformers and conductors, potentially shortening their lifespan. Furthermore, the lack of a neutral can make it difficult to provide proper overcurrent protection for single-phase loads. In a typical single-phase system, the neutral conductor is used as a current return path, and overcurrent protection devices are typically installed in both the phase and neutral conductors. However, in a delta system without a neutral, there is no neutral conductor to protect, which can make it difficult to provide adequate overcurrent protection. Given these safety, code compliance, and equipment performance concerns, it is generally not recommended to use a 115 volts three-phase delta system without a neutral for powering single-phase loads. A more suitable approach is to use a Y-connected transformer, which provides a neutral conductor that can be used to supply single-phase loads. A Y-connected system allows for balanced loading, proper grounding, and compliance with NEC requirements for grounded neutral conductors at outlets. If a delta system is avoidable, careful consideration must be given to load balancing, grounding, and the potential hazards associated with single-phase loads. It may be necessary to consult with a qualified electrical engineer to develop a safe and code-compliant solution. Let's explore practical alternatives to using a 115 volts three-phase delta system without a neutral, specifically focusing on scenarios where powering 115 volts outlets is required. The primary alternative, as previously mentioned, is employing a Y-connected transformer. A Y-connected transformer features a neutral point, which is the common connection point of the three-phase windings. This neutral point can be grounded, providing a stable reference point for voltage and facilitating the creation of single-phase circuits. When using a Y-connected transformer, the 115 volts outlets can be connected between one of the phase conductors and the neutral conductor. This configuration provides a safe and code-compliant way to power single-phase loads from a three-phase system. The neutral conductor provides a dedicated return path for current, minimizing the risk of unintentional neutral connections and facilitating ground fault detection. Furthermore, a Y-connected system allows for balanced loading, as the single-phase loads can be distributed across the three phases to minimize voltage imbalances. Another alternative is to use a single-phase transformer. If the primary power source is three-phase, a single-phase transformer can be used to step down the voltage to 115 volts for the outlets. The primary side of the transformer would be connected to two of the three-phase conductors, while the secondary side would provide the 115 volt single-phase power. This approach eliminates the need for a neutral conductor, as the single-phase system operates independently of the three-phase system. However, it is important to ensure that the single-phase transformer is properly sized to handle the load of the outlets. A third alternative is to use a rotary phase converter. A rotary phase converter is a device that converts single-phase power into three-phase power. This can be useful in situations where only single-phase power is available, but three-phase equipment needs to be powered. A rotary phase converter can be used to create a three-phase delta system, which can then be used to power the 115 volts outlets. However, it is important to note that rotary phase converters typically produce unbalanced three-phase power, which can lead to voltage imbalances and other problems. Therefore, it is important to choose a high-quality rotary phase converter and to carefully balance the loads in the three phases. In addition to these alternatives, there are also several specialized transformers that can be used to create a neutral conductor in a delta system. One such transformer is a zigzag transformer. A zigzag transformer is a special type of transformer that is designed to create a neutral point from a three-phase delta system. The zigzag transformer has three windings, each of which is connected to one of the three-phase conductors. The windings are arranged in a zigzag pattern, which creates a neutral point at the center of the transformer. This neutral point can be grounded, providing a stable reference point for voltage and facilitating the creation of single-phase circuits. Another specialized transformer is a grounding transformer. A grounding transformer is a transformer that is specifically designed to provide a grounding path for a three-phase delta system. The grounding transformer typically has a delta-connected primary winding and a Y-connected secondary winding. The neutral point of the secondary winding is grounded, providing a low impedance path for ground fault current. This helps to protect equipment from damage and to prevent electrical shocks. When selecting an alternative to a 115 volts three-phase delta system without a neutral, it is important to consider the following factors. Firstly, the available power source must be considered. Is the available power source three-phase or single-phase? If the power source is three-phase, a Y-connected transformer or a single-phase transformer may be the best option. If the power source is single-phase, a rotary phase converter may be necessary. Secondly, the load requirements must be considered. How many outlets need to be powered, and what is the total load of the outlets? The alternative chosen must be able to handle the load requirements. Thirdly, the safety requirements must be considered. The alternative chosen must provide a safe and code-compliant way to power the outlets. This includes providing a dedicated return path for current, facilitating ground fault detection, and minimizing the risk of unintentional neutral connections. Fourthly, the cost must be considered. The cost of the alternative chosen should be weighed against the benefits. Some alternatives, such as zigzag transformers and grounding transformers, can be relatively expensive. Finally, the complexity must be considered. The alternative chosen should be relatively simple to install and maintain. Some alternatives, such as rotary phase converters, can be complex to install and may require specialized knowledge. In conclusion, while using a 115 volts three-phase delta system without a neutral may seem like a viable option in some situations, it is generally not recommended due to safety, code compliance, and equipment performance concerns. There are several practical alternatives available, such as Y-connected transformers, single-phase transformers, rotary phase converters, zigzag transformers, and grounding transformers. When selecting an alternative, it is important to consider the available power source, the load requirements, the safety requirements, the cost, and the complexity. By carefully considering these factors, it is possible to choose an alternative that provides a safe, code-compliant, and reliable way to power 115 volts outlets from a three-phase system.